for it?
You
Or
could. You only need 2 letters though for a line. So you would generally use the endpoints for that. So you generally use the endpoints.
okay, generally use the endpoints.
Is this okay? Do you have this down in your notes?
Yeah, I just wrote it down.
Okay. So next we're going to talk about a chord or a chord. It's got an H that's silent. So a chord, like a diameter, it starts and stops on the circle, but it does not go through the center. So very important here is again that it starts and stops on the circle, but does not go through the center.
Starts and stops on the circle, doesn't go through center. All right.
Like when you sometimes when people cut an apple, they don't go through the center, they just chop off those little side piece. Whereas if you cut it right down the middle, then it's a diameter. Any questions on those 3 things?
No, not yet.
Okay, so here's a problem for you to try. We'll go A. Okay, so this is center C. And we'll go here. Okay, so I want 2 radiuses and 2 chords.
I guess you could say CT and CA.
Okay.
And a chord S and A.
Okay, is there another chord?
A and T.
Yes. Any questions on that?
No.
Okay, so we're going to talk about arcs next, I guess. I guess that's the next most. It's like you're given some of the things, but you're not given all of them. Okay, so there are 2 types of arcs that you need to know about. Okay, so this is considered a minor arc, and I'm going to give it some letters here. So minor arc AT. So AT, this arc, it means it's this piece right here. Okay, but it also refers to this sort of this central angle here, which we'll get to in a moment. But there's 2 types of arcs that you might see, and the first one is a minor arc. Okay, so minor arcs have a measure. This is very important. Have a measure of less than 180 degrees.
Have a measure less than 180. Okay.
Okay.
And then.
So minor arc will be next. Did you have a question?
So how do you locate the fact that it's a minor arc?
You visually notice that for it to be a minor arc, it has to be less than 180 degrees, which means it can't go
straight
counterclockwise. It has to go the shortest distance between those 2 points.
Okay.
Like if I ask you to fly from Phoenix to New York, you fly across the continental US, you don't fly around the world.
You don't fly over all Asia and Europe.
Yeah, exactly. That would be ridiculous. I mean, well, it wouldn't be the fastest, we'll say. Maybe not ridiculous. Okay. So a major arc requires 3 letters. Okay, so we're gonna kind of label this again the same. So we'll go S, A, T, and this will be O right there.
Uh-huh.
So major arc SAT. Okay,
Let's
first
see.
thing is you need to use 3 letters. And the reason is the letters give you the path. They say it goes from S to A to T. S to A to T.
S to A to T.
Because if I just said ST, do you know if it's the short one or
Yeah, that
the
would be a
bigger one?
minor one
Right.
because it's getting there quick as possible.
Yes. Okay. So in full disclosure, they don't actually say major or minor arc. You're supposed to know if it's AT 2 letters that it's the minor one, and if it's 3 letters, it's the major one. And this one has a measure greater than 180 degrees, but less than 360.
It's a measure greater than 180 but less than 360. Okay. All right. Yeah, that makes sense.
Good. Okay. So those are arcs. Okay. Now, the thing you might that I think this leads to is if you take a circle and you have a diameter and you cut this thing right in half. Actually, let's not draw it that way. Let's draw it horizontal. This is 180 degrees. This is 180 degrees. So there's a total of 360 degrees in a circle. But if we're just interested in a semicircle, which is half the circle, that's 180 degrees in a semicircle or half circle.
Half circle. All right. Yeah, I guess that makes sense. 180,
Okay.
180.
Okay. So let's do another kind of one of these synthesis problems, see what you're understanding or not understanding. So let me go A, C, T, S. Okay, so let's actually I need to do one more thing here. Do that one right there. Okay, so I first want a radius, a diameter, and a chord. Just one will do of each, please.
All right. I guess you'd say radius is A to S,
Okay, so it's a line segment AS. Yep.
and then a chord is C to T,
Okay, good.
and then diameter is, you could say it has the
You can only give me 2 letters. 2 letters. Go ahead.
like large diameter.
There's only one diameter.
Um,
If you need to go back in your notes and look at the definition of a diameter, or I can tell you verbally whatever would be best.
yeah, I can check real quick. Um, diameter. Sorry, could you just tell me because
Sure. I'm gonna go back and show you as well as tell you. So a diameter starts and stops on the circle and goes through the center. Starts
okay.
on the circle, ends in the circle, and goes through the center. It's like you said, it's 2 radii, but they have to be like completely opposite if you want
Mhm.
to use words like that.
It's like 180 in a sense, right?
Yes.
Okay.
Okay. And okay, I didn't draw this great, but I think more people than not would say there is a diameter here.
Uh-huh. Yeah, that would diameter would be like SAT.
It's only 2 letters though. Can only
Or
use 2 letters.
S to T.
S to T. Okay. Now I want you to find me a minor arc. And you have to do this visually. You have to sort of say, okay, that looks like less than 180, or that looks greater than 180.
Mhm.
I want one minor arc.
I guess you could say S to C.
Good. Now this one is more of a curved hat above it,
Mhm.
line, curve. I don't know. It's not a line anymore. Okay.
All
Do you
right.
notice that C to T is also a minor arc?
Yeah, I do.
Okay. Now S to C to T is
Uh,
180 degrees.
yeah.
It's neither a minor nor a
A
major
major.
arc. Okay,
What
but
would
there
I
is
usually call it? Would I just say like 1/800?
you wouldn't call it anything. You wouldn't be asked that. Um, but there is at least one major arc here, and it's always a path, like you said before, S to T. It's got 3 letters. Can you come up with one major arc here for me?
You could say CTS
Okay, I agree. How
or
about this one?
STT.
How about, sorry, go ahead.
Oh, nothing. I was just
Did you have
repeating
another
it.
one?
I was thinking maybe like wait, no, that wouldn't work. I was gonna say S to C, but then that's like boom right there.
How
I
about
guess we
CST?
C.
C to S to T.
Oh, yeah, that's true. Actually, you could do that.
Yeah,
And then I guess you could also do TSC if you wanted, but
that's so the forwards and the backwards is the same.
mhm.
So it's not any different than the one that I gave you, but it is correct.
Oh,
It is correct. Like you can put that down. It's just not a different one.
uh-huh. Okay. Yeah, I didn't know that rule. That's interesting.
Okay, now if we're going to talk, the one last thing to talk about here, um, here's a circle. This is a tangent line. A tangent line hits the circle exactly once. And you can think of it as like touches, or
Mhm.
bounces. So the analogous thing is if you recall when we were graphing quadratics, the parent function would come down and it would just touch right there, touch and kind of bounce off. That's what a tangent is. A tangent, it only hits in that one spot perfectly.
Uh-huh. So it's just a 1 point connect.
Yes, yes,
And it's always outside of the circle, correct?
yes, it has to be. Has to be on the out, it's sort of the outside of the edge.
All right.
Now, I know it's not listed, but we might as well talk about it because this is important. If you hit a circle in 2 places, this is called a secant line.
A secant line.
Yeah.
How often do you see those, you'd say?
You will see them, I mean, shortly. I'm surprised they're going in this direction, but it is correct what they're doing. They've left off sort of the another, this one's very important to have.
Yeah. Well, I'm glad that I have you so I can learn it.
Yeah. Okay, so let's now talk about some problems. We did not talk about concentric circles, but I don't know what they're, we'll see if that comes back. So let's go to that first page that you just said. I'll snip in a question and we'll take a look at it. Okay, rays M and N are tangent to circle P. So what that means, let me use a different color here.
Mhm.
They're starting over here, they shoot off, and boy, that was not drawn well. They only hit the circle in that one place.
In that one spot, yeah.
Yeah, okay, so they tangent, they just touch there. Now, did you draw this red one in or did your instructor do that?
My instructor did that.
Okay, so there's this definition that says uh, a tangent, I don't want to say this, a tangent to a circle, which is what you have in both these
Mhm.
cases. Uh, or actually, I think it's written this way: the radius that meets a tangent to a circle. So see how P to here, let's call this point A. This radius PA meets this tangent. They always meet at 90 degrees.
Mhm.
So let's go back to
Oh,
my drawing up here. If I were to draw a radius right there, this is 90 degrees. So the radius to the tangent is always 90 degrees. So here, this radius P to, we'll call it B,
P to
and
P.
this tangent is always 90 degrees.
Okay. Always 90 degrees.
Yes.
And then it's 90 degrees on both sides, correct?
Yes, because the tangent to the radius is always 90 degrees.
Is it ever possible for the tangent to create a triangle?
Yes. I mean, yes, there you will see problems like that.
So then how would I make, if there's the 290 degrees, then how would I make it be the like 180 for the triangle total, like with the other point? Would the other
Uh,
point just
we
be
we
zero?
don't. So the other triangle you're thinking, I mean, I think what you're thinking of is what you see in problem two, but there is this triangle. I don't know if
Oh,
that's what you're asking about. Yep.
yeah.
That doesn't really apply to this one. Kind of does, but I guess I'm not sure what you're asking it. I guess could you try
It's
again?
so
Could you
it's
try?
like the to find point W, like I looked at the like the shape is like a kite.
Mm-hmm.
And then I know that there's like 90 and 90 is 180 plus 130 is 180 plus 130, that's like 310.
Yes.
And then to make it be the total area of like a kite is like a one, two, three, four. I'm trying to remember.
360.
Yeah, 360. So then if I have 310 and then I need the 50 more to like for W, so like W would be like 50 degrees, I'm pretty sure.
Yes.
And then so like the part is with that is what if like that's just because it's a kite, like I'm going up to that number. But what if I'm just trying to get like a triangle?
So
And
you're talking about problem two, and there's actually like I don't know if this is what your instructor. There are some formulas here that I can show you, but let's do what you just said in problem two.
okay.
Maybe maybe your instructor isn't. I don't know. Well, I'll address that in a moment. Let's look at number two. Yeah, so kind of it's to give a partial answer is like everything is in play. So if you see a triangle or a quadrilateral, which I think is the word you were looking for, then you
Uh-huh.
can use those sum properties. Okay. Now this is a triangle that I've drawn, and this other angle is also x.
So that other angle is also X, yeah.
Yes. Now there is a theorem that allows you to do that. You're not tested on that anymore, but you have to be careful here. Like this one is drawn reasonably well so that you can assume that, but be careful.
Uh-huh. 70 plus X equals 180. So I guess you'd have to say that it's like 55.
Yeah, x is 55.
Yeah, that's kind of what I was asking, I guess.
What would angle y be?
Angle Y. Does it have to, am I using 55 to make it add up to 180 once again?
Yes.
Is that called a linear pair?
Yes.
I think I'd make Y become 125.
Right. So that's still in play from last semester.
Mm-hmm.
Okay, let's look at another problem here, number three.
Number 3.
Ray K is tangent to circle R. Ray K is tangent to circle R. So there's, let me draw it here, a different color. This is tangent to circle R. This is a radius. What is the angle measure right here when a
Um,
radius meets a tangent?
90 degrees.
90 degrees. Very good. You have to start, going that direction, or, I hate to say assume, but you want to, like, if it looks it, if you feel like that's right, that's the only way you're gonna be able to do these problems going forward, is you gotta, be able to have some clarity on that. So 120 is kind of this angle right here.
Mhm.
What I'll call X right there? What is X? If this other angle is
I
120.
I guess it would have to be 60, right?
That's right, it's 60.
So then that would be 150 total. I would have to be 30 degrees.
Very good.
Yeah, this is easier doing it the second time now.
Yeah, now you're learning some things though along the way to be able to answer that.
Yeah. So then
Okay, so on number 4.
number four, yeah, number four would be good.
All right, let me get that snipped in. Okay, so it says line T is tangent to both circles. So this is very similar to what we just did. A tangent to a radius produces what? What kind of
Uh,
angle?
90 degrees.
And then over here,
I guess that would also be 90 degrees.
so this is a quadrilateral. Quadrilateral is like a rectangular square. It has 360 degrees. So
360,
so the four angles have to add up to,
360. So
yeah.
we already know that we have let's see, that's 180 plus 75, that's 155. I mean 255.
So
And then
let me give you a suggestion. 180, like you said, if you
uh,
subtract that, it gets down to 75 plus Z equals 180.
oh, that's an easier way to do it. That would
Yeah.
be 105.
Yes.
And then
That's it.
use 105. Yeah, I kind of like
Yes.
this tangent thing. It makes you have to guess less.
Yes.
I'm just so curious on like how people can think of all this and just make it all work.
Yeah, that's a good question. The so there's one of these unexplained things that I was watching. This guy built this garden in Florida out of coral reef stuff, I believe.
Uh-huh.
It's really heavy stuff, and he moved it all himself, supposedly, with very primitive things. Um, a lot of what he did is derived from circles and using relationships like these. So there's a lot going on here that helps you,
Uh-huh.
but we don't use it today. But if you didn't have a computer, you would be forced into this world of trying to do things with circles. I mean, you maybe have heard of grinding stones.
Yeah.
I mean, these are two grinding stones.
Well, I guess that's true actually.
I mean, they're all over the place. We just don't care anymore. We
Yeah.
moved on. All right. Now, so this problem. So you're kind of like, the instructor is kind of like going around actually telling you what you're doing here, because there's some formulas that I haven't given you yet that I think might have been more useful, but we'll just keep going here. So quadrilateral post is circumscribed. So circumscribed, you got to remember, means on the outside. The other one you might see is inscribed. Obviously, that's inside.
Inside.
And you've said a few times up near the test, we've done some vocabulary. It might be good to get started earlier on making your vocabulary lists for the chapter.
Yeah.
Okay. So you need a little bit more information to be able to do this. So if you have a circle and you have a point here outside the circle,
Mhm.
and you draw two tangents from this same point, these tangents are always congruent.
So those two tangents are always congruent.
Yeah, so it doesn't matter. Like, let's say I
Oh, right,
choose,
because it's always 90 degrees, right?
well, it's more, it's not the degree, it's the lengths. The lengths are the same.
Oh,
So these lengths are the same. See how they're longer? These are longer than
yeah.
the ones in red are longer. So what I'm trying to show you is that from a point, if you have two tangents from that point, the line segments are always congruent.
The line segments are always congruent.
Okay, now let's go back and look at another problem that did real quick here. See this problem here where we started at, I'll call this P. P to A is congruent to P to B.
P to A is congruent to P to B.
Now, do you see that the radiuses are congruent?
Um,
They have to be. Radiuses are always congruent.
yeah.
Now, if you draw a line from P to, oh, I can't use P. Let me make that B. So if you draw a line from P to B, do you see how it's congruent to itself?
Yeah.
And you have two triangles that are congruent by side, side, side.
Uh-huh.
So you can get the congruence from a bunch of different ways. You actually end up using side angle side to get it, but that's how they prove that the tangents are congruent.
All right.
So I'm
Yeah,
gonna
I see that.
so I'm gonna go. We're gonna start this post problem a little bit differently. I want you to follow along what I'm doing here first. So here's A, and here's C, and here's point P. So this right here, P to A is the same as P to C. Do you see that? Do you agree with that?
Yes.
Okay, for what we just said. Now A to O, get O a little bit more out here. A to O is congruent to O to R.
All right. I see that as well.
Now the reason I've drawn these all with a single line is because originally P to A was congruent to A to O. Now from if we keep going here, here's S. S to R is the same as S to D.
And then C to whatever the next one
Yeah,
is.
this is T. So C to T, which is given as double line, is the same as T to D. Now in the problem, it tells you that O to R is 13. 13, 13, 13, 13. And then it tells you that S to T is 12. Where's S to T? Oh, that's the big one.
Uh-huh.
So that means they're each 6. I guess that's not drawn to scale. Okay.
Huh.
I mean, it works, but
Yeah. So then,
so the perimeter. Sorry, go ahead.
am I gonna add all those numbers up together?
Yes.
And is that what you're saying about the perimeter? Okay.
So I probably would multiply 4 times 13 because there's 4 of them. 4 times 6.
That's 24 and 52, 76.
Yeah.
Okay, 76 inches. Add it all together. So I just have to understand with this one that many of the sides are the same.
You have to understand that from a point outside the circle, the two tangents are always congruent.
The two tangents are always congruent. All right, yeah, I definitely see that.
So like I think some of this makes sense more in like think of like space, like here's Earth, and then you're here, and you want to get whether you want to go to the top or the bottom, it's exactly the same length to get there.
Yeah.
That's what we're saying. That's the takeaway. And it just, in this problem, they're just giving you more. In this previous problem, they're just giving you more tangents, but they're
Mhm.
all points to a tangent.
They're all points to a tangent. Yeah.
Okay, I'd like to talk next about inscribed angles, or I'm sorry, central angles and inscribed angles and arcs.
That I agree with that.
Okay. So let's go here. I'm going to draw a circle again. Here's a circle. And here's a slice of pizza. And I'm going to say that this is 60 degrees. So that 60 degrees is what's called the central angle. The reason it's called a central angle is because the vertex is made at the center of the circle. A central angle has its vertex at the center of the circle.
Central angle has its vertex at the center of the circle.
Now let's look at the measure of arc ZW. So when you put a little m in front, that means the measure of arc ZW. Is this a minor arc or a major arc?
That is a minor arc.
Okay, so the measure of this arc is 60 degrees. And this is very important, very important. It's kind of a thing you'd want to put in your notes here as a reference. And what it is that the measure of the central angle, oops, that's really poorly drawn. Whatever that central angle is, the measure of this arc is also
The same thing.
yes, but only for a central angle.
Does it matter how big the arc is?
No, it actually, like, it works over here too.
Okay, cool.
Okay, so that's a central angle. We just talked about a central angle. Now we're going to talk about an inscribed angle. So we're going to draw a circle. This time the vertex is on the circle. So that's the key difference between them. For an inscribed angle, the vertex is on the circle.
Vertex is on the circle. Okay. Does it have the does it work the same for as the
Well, so let me, we got to give you some numbers. Let's say this is 40 degrees. This angle down here is 20 degrees.
So am I looking at it as it's half or getting multiplied? Like which one?
Well, it depends. I like to label the angle as x, and then this is 2x. But you can go either way. You can call the one on the outside on the arc x, and then it's half.
So the outside will always be like
Bigger.
twice the size.
Yes. And I think visually you can see that. You can see that, like, this looks smaller than this arc, well, they're not related.
Yeah, I guess that's true actually.
All right. So the reason this is important is it allows you to do some, like, new problems now that we previously were not able to do. Although I'm not seeing any that are all that good to start with. Let me just make one up real quick, and then we'll jump to one of the ones you got here.
All right.
So here's a kind of a starter problem here. Let's say that the measure of arc ST is 80 degrees. What is the measure of arc SRT?
It would have to be 280 degrees.
Yes.
And then would
Now,
I look
similarly, what is I'm sorry, what is the measure of angle SAT?
um 80 degrees.
Okay. And then it's a little bit harder because we assume that that's the this one right here, but I could also ask you about this other angle, which is a little harder to,
Oh,
but it's 280.
280. Or R is 280, correct? Or
Uh,
the angle A is
yeah,
2.
yeah, the whole angle, yeah. I mean, this it's kind of unclear um what it is. They almost always ask for the smaller one.
Uh-huh. That's how I've been taught for it. I didn't even know I
Yeah.
could do the other side till right now.
Yeah. So the way that you would use this is in like the kind of this warm up problem where they ask you for the parts of the requested circle. Let me see if there's one you haven't done yet, though, that we can. Did you send me another? No, you just sent that. Okay.
I can try and find another one for you
We're
though.
we're kind of short on time.
Yeah.
Just we'll just go with what you've got here.
Yeah, I think I'll probably try and schedule another meeting for tomorrow.
Okay, sounds good. All right, sorry, let me it's going back and forth. Okay. Here we go. All right, so here we go. So let's not, I'm just ignore that for the moment. So they give you that this interior angle COA, that's an A. So the measure of angle COA is 107 degrees. That's given. And then similar, the measure of angle AOB is 49 degrees. Okay, so now if I were to ask you the measure of arc CA, what is the measure of arc CA?
107.
107 degrees. How about if I ask you for the measure of arc? Well, let me not do that. Measure of arc AB. We'll just do that one
Uh,
next.
49.
49 degrees. Good. Okay. So now the other side of this circle, and we can go, we have to give it a letter, as I was trying to do here. If I wanted the measure of arc CEB, we know that if you go all the way around the circle, if you go from C and you go all the way around, it's 360. So we've got to subtract out the 107 and the
49 from 360,
49.
correct?
Yes. And that gives you
153 minus 49, that's 104. I'm pretty sure.
yes, 204.
Oh, my bad.
Yeah, you had it right, and I covered it up. Okay. So I mean that's kind of a problem you'll get. Here's kind of another problem you might see. Let me see if I can get this right. They'll tell you that this is 50 degrees. And then, yeah, okay. So let's call this SAT, and then we'll go C here. Okay, so what is the measure of angle SAT?
50 degrees.
50 degrees. And what if I tell you, I'm going to tell you now that the measure of arc SC is 130 degrees. Okay,
Then
so
I would,
so can you now tell me the measure of arc TC?
I guess it would have to be 80.
Yes. Very good. So this is 80 degrees. So what is the measure of angle TAC?
That would also be 80 degrees.
I messed this up. I apologize.
Oh,
This is 25. Sorry, I messed that up.
all good, all good.
It's the inscribed angle. The inscribed angle is always half, or you got to double it. So this TAC is an inscribed angle, so it's half of 80 or 40 degrees. And then I guess the last thing I could ask you here is SAC. going the other way round, and you'll find that that's 230.
230 because I added it as. Wait,
Yes.
would it be 230 or 220?
It's 50 plus 80 plus something else to get to 330, 360. So it's,
260.
yeah.
Okay.